Hi, hello, welcome to my channel, Dr. VRK Reddy. Channel handle is at VRK Reddy underscore math sci-tech. So please do subscribe this channel to get latest updates on mathematical videos, and that covers a lot of math contents that is useful to the students and the teachers. Today I'll be making a video on matrix theory. Matrices are very important in our life. See, matrix theory is used in cryptography that can actually encrypt the data and also used for the decryption in the cryptography. Similarly, that will be used in computer where image can be rotate or translate in different forms like one position to another position, and all these contraction and all these are important for image in graphics. Also, this matrix theory is useful in data science to process the data, to analyze the data, to store the data. Therefore, this matrix theory is having lot of applications. This video is made for especially BBA students and finance students, commerce students, and school students, those who want to learn matrix theory. Also, a basic information will also helpful to the college students, those who want to learn and understand what are matrices and properties involved in it, types of matrices and some operations on it. Let me take you to the matrix theory. The term matrix was introduced by James Joseph Sylvester in 1850. Further, the theory was developed by Arthur Cayley in the 19th century. So they have given a significant contribution to the matrix theory. Today I'll be explaining what is a matrix. The matrix by definition is arranging numbers equations in the form of rows and columns. That is, something is of this form. We call it, these are rows. These are actually rows, and these are called columns. So vertical lines are called the columns, horizontal lines are called the rows. So for example, A is equal to 1, 2, 3, 4. Then you call these lines vertical lines. Are called columns. The horizontal lines, these are the horizontal lines. Are called rows. So if you look at that A is having 2 rows and 2 columns. We read A as 2 by 2 matrix. Or you can say that 2 by 2. This stands for by. Of course, it looks like multiplication symbol, but this is actually by. So 2 by 2 matrix. So suppose you take a matrix, suppose A is equal to 1, 2, 3, 4, 5, 6, 7, 8. And now you look at that number of rows 1, 2, row 1, row 2, row 1, row 2. Therefore, 2 rows are there. A is a 2 by columns. You look at that first column C1, C2, C3 and then C4. Therefore, 4 columns are there. A is a 2 by 4 matrix. A is a 2 by 4 matrix. 2 by 4 matrix. So, if you understand what are rows and columns of a given matrix, what is the size of A, so or you can order of a matrix, So, order of a matrix is nothing but number of rows by number of columns of a number of rows and number of columns of a matrix. This is how you are saying that matrix is of size, which size or which order it is. Now, moving back to some properties like how do you add addition, and we have operations addition, multiplication, subtraction. We have addition and then this is subtraction, and then multiplication. We have another operator division, but this is used in different way, like inverse. We will see how to handle that, like inverse. We will see how to operate or how to use this operation later of the course. So, firstly I want to focus how do you add addition or subtraction of two matrices. So, when do you add two matrices or when do you subtract one from the other? Suppose A is equal to 2 by 4, 2 by 2 matrix. A is a 2 by 2 matrix. Suppose A is a 2 by 2 matrix and B is equal to is also a 2 by 2 matrix. Then I can write A plus B is equal to 1, 2, 3, 4 plus 3, 7, 8, 9, the numbers given in the matrix B. Now, you have to understand something. So, you have to look at that. This is in the first row, first column, row 1, C1, and this element is also in the row 1, C1. Therefore, you can add row 1, C1 elements only, that is 1 plus 3 you are writing. Now, look at that, the second one, it is row 1 and but it is C2. So, you call similarly, you look at that, this is row 1 and then C2. Same position you have to map with within the first and then second matrices, then you add them, therefore 2 plus 7. Now, you look at that, the other one, that is 3 is in row 2 but is in C1, you should add row 2 and then C1, that is 3 plus 8, and next you have one more element, that is 4. This is row 2 but this is C2. So, same correspondence you should see row 2 and then C2 in B, because we are adding B to A 8. Therefore, 4 plus 9. Now, you have to simplify further, that is 4, 9, 11 and then 13. This is again a 2 by 2 matrix. You see that whenever you are adding, you are getting the output is of same kind, 2 by 2 matrix. Secondly, I am trying to find A minus B. Same matrix A minus subtraction. I am trying to understand how to apply that. It is again element by element, of course, with respect to the position. What is the position of these entries? So, position of this one and this one is row 1 C1. This is also row 1 C1. Therefore, 1 minus 3 because A comes first. This is A and this is B. Therefore, A element first placing and then subtracting B element from A. Similarly, if you look at this entry, this is row 1 and then C2. The corresponding element in B is row 1 and then C2 is 2 minus 7. Similarly, if you look at 3 is in row 2 C2, therefore 3 minus row 2 C2 in the second matrix, 3 minus 8. Similarly, you have row 4 C2, sorry, row 2 C2, row 2 C2, row 2 C2. You have similarly row 2 C2 in the first matrix A and row 2 C2 in the second matrix, therefore 4 minus 7. This implies an output of minus 2 and then minus 5 and similarly you have minus 5. This is the matrix subtraction of B from A. You are getting an output like this. So, this is how we are applying the row addition and subtraction of two matrices. Now, so can you write matrix A is equal to 1, 2, 3, 4? Because I was trying to see that can I write it? Can I write it? Answer is no. You should not use any commas. You shouldn't use any commas. You should not use any comma. Therefore, 1, 2, 3, 4. You look at that, writing second row elements exactly under the first row elements and move on for further rows also. Therefore, it is you have to identify the location of a column and you should write it. All elements must be under the same elements and it should follow that. Okay. Now, before I introduce multiplication, so another question, can I add A is 2 by 3 matrix, B is a 3 by 2 matrix. Can I add A and B here? That is A plus B. Is it possible? Is it possible? Answer is no. Answer is no. Of course, I can keep A plus or minus B. A plus or minus B is possible whenever A and B are of same ordered or same size matrices. That is, if A is 5 by 5 matrix, then A plus or minus B is possible whenever B is also a 5 by 5 matrix. Otherwise, it is not possible. Therefore, this is more important, that is size of A must be coincide with size of B. Actually, B is also 5 by 5 for addition and subtraction, for addition and subtraction. Now, before I take you to the multiplication, I would like to introduce actually a small concept called, if you look at your school math, if you are trying to look at your school math where we have the problems like you are purchasing some pens, suppose you are buying 2 blue pens and then 5 red pens which cost you around 150 rupees, and then your friend is purchasing like 3 blue pens and then 4 black pens, sorry, four red pens, that is around 120 rupees. Now what is the cost of blue and red pens? So to find it, you have to use the concept of elimination procedure. That is, from here I can write 2b is equal to 150 minus 5r, and that implies b is equal to 150 minus 5r divided by 2. You use this here into 3 times 150 minus 5r divided by 2 plus 4r is equal to 120. Then after eliminating, you will be getting the pens. I mean, that is 450 minus, substitute r in b is equal to 150 minus 5 into r place to get b value. This is the standard procedure to eliminate it. Or if you don't want to use this particular method, substituting the other value, then I can do the other method, that is, so this is one set of equations. The other set of equation is 120. Now I want to eliminate b first. To eliminate b, I am multiplying this entire equation with 3, the entire equation with 3, and this entire equation with 2. This implies 15r, sorry, this implies 6b plus 15r is equal to 450, and further this gives you 16b plus 8r is equal to 240, and now subtract, it is giving 7r is equal to 210. Therefore, you can get r and then substitute in the other value, and then you will be getting the blue pen. So this is another way, but instead of using these techniques, you want to handle them in different way. That is called the matrix form. That is, there are 2 variables. I say that whatever are the variables I am writing in a column form, and whatever on the right hand side I am writing in the matrix form. See, now I have to adjust a little to get the above equations. That is, those are called the coefficients. In the first row, if you look at this, the 2 is one coefficient for b, 5 is another coefficient for r, and 3 is another coefficient in the second row, 4 is the another coefficient of r in the second row, second column. So now you see that perfectly it is matching. This is the first row, and you multiply this data with this and equate it to 150. That is 2 into b plus 5 into r. You may ask, since if there is no sign, it means plus only. If there is no sign, it means plus only. Therefore, I am writing 5 plus 5r is equal to 150. Similarly, I am multiplying this with, again in the same order, that is 3 must be b, 3 must be multiplied with b, and 4 must be multiplied with r is equal to 120. In other words, whenever you do that, 2b plus 5r and 3b plus 4r, 150, this is. If you equate, then you are getting exactly that. Here, whenever you are representing a matrix, for any matrix, we use square brackets or open brackets. That is, either I can represent this way or this way. So both are standing for the same thing. Now, after understanding this multiplication, now I can give you A is equal to 1, 2, 3, 4 and then B is equal to 5, 6, 7, 8. What is A into B, or you can call it AB. So AB means product. If nothing is there, that means product. A into B is equal to 1, 2, 3, 4, 5, 6, 7, 8. According to the definition which we have seen earlier, this row must be used to multiply this column. That is 1 into 5 plus 2 into 7. Once that is done earlier, we don't have any further columns, but fortunately or unfortunately we have extra thing. So fortunate is to learn the more concept. Unfortunate thing is that you have to perform extra calculations. So therefore you have to shift to the second column. So this is C1, this is C2. Since you have completed whatever you can write it, you have done in the C1. Now you are moving to C2. In the C2, 1 into 6 plus 2 into 8 is there. Similarly, once that is exhausted, no further columns are there. Next I am moving to row 2. So row 2 into C1, that is 3 into 5 plus 4 into 7. Now it is done. It is closed. C1 is done. Next I have to move to C2. That is 3 into 6 plus 4 into 8. You look at that whenever you are actually operating these operations, you must be aware of that. This 5s and then 7. This is first column. First column must be appearing only in the first column of that multiplication. And 6 and 8 must be appearing only in the second column. This is C2. This set is in C2. Please try to observe that. So 6 below 6 and 8 below 8, since there are two elements. So therefore, this is how we are doing. And also further, if you want to look at that, the further observations, that is, you see that this is row 1. This is row 1. Row 1 terms are only appearing in the row 1 everywhere, 1 and 6. You can see those are appearing only in the, this is row 1, this is row 1, this is, all are appearing in row 1 only. If you look at row 2, that is this, these are the row 2 elements that are appearing in the row 2 of the resultant matrix. Now if you simplify, that is exactly equal to 5 plus 14 and 6 plus 16 and then 15 plus 28. Next one is 18 plus 32. So now with this I can say it is 19, 22 and then 43 and then this is 50. This is my matrix. How many rows are there? 2 rows, 2 columns. We call it 2 by 2 matrix. We started A is 2 by 2 matrix, B is 2 by 2 matrix. Still we are getting a 2 by 2 matrix. Now the question is that, can I get different matrix whenever I am multiplying different matrices? That means whenever A and B should have same sign, same order for multiplication. Answer is no. No need to have same order. Like in the addition and subtraction, both must be of same order. But now you no need to have same order. You can go with different orders. In this case, A can be 3 by 2 matrix, B can be 2 by 3 matrix. In this case, you can get AB as 3 by 3 matrix. matrix. That is, you should observe that the columns and then rows must be matching. Then the output is this stands for rows, the resultant matrix columns. Now you are getting A rows, B columns. So that is the output of the product. So for example, for the matrix, for this same A and B, can I calculate BA is the question. Answer is BA. Answer is yes, because B is 2 by 3 matrix, A is 3 by 2 matrix. Now you can see the rows, columns of B are matching with rows of A. So the output is BA is equal to, these two are actually merging and then giving a 2 by 2 matrix. You can check that. Suppose if A is 2 by 2 matrix, but B is 3 by 2. Can I calculate AB? Can I calculate BA? So answer AB is not possible as A is 2 by 2, B is 3 by 2. Now you see here, these two numbers are different. This one and this one are not same. Therefore AB is not possible. This implies AB is not possible to calculate it. However, if you look at BA, that is, B is a 3 by 2 matrix, A is 2 by 2 matrix. Now you look at this, here you have 2, 2, both are matching. That is, columns of B, rows of A matching. That is giving BA as 3 by 2 matrix. Is well defined. Previous case it was not defined. Now it is well defined. So examples we will see. Examples. Suppose A is 2, 3, 4, 5, 6, 7. It is a 2 by 3, and B is equal to 1, 2, 3, 4. It is a 2 by 2 matrix. Now I will tell you the reason for it. If I attempt AB, so 2, 3, 4, 5, 6, 7, that is 2 by 3, and 1, 2, 3, 4 I am having. This is 2, 2. Why it is not mapping? Why it is not possible? You can check it easily. See, you can apply. So first row with columns, right? First row with columns. In this process, you can see 1 can be used for 1 into 1. 3 can multiply with 3 plus 3 into 3 plus what about 4? There is no entry here. There is no entry here to supply here to get the output. Therefore, AB is not possible. AB is not possible. Also, you can see A is 2 by 3 and B is 2 by 2. These two are different. I mean, these two are of not same. This is, one is different, this one is different, and then this one is different. Both are not same. Both numbers are not same. Therefore, you cannot multiply. Suppose you reverse the role. We will see BA. BA is 1, 2, 3, 4, and then 1, 3, 4, 5, 6, 7. Let's see that output. These are the rows, these are the columns. So columns 1, column 2, column 3. This is row 1. This is R1. Now you have to multiply R1 with C1. That is 1 into 1 plus 2 into 5. That is done. Next you are moving to second R1 with C2. That is 1 into 3 plus 2 into 6. 1 into 3 plus. So if you move to there, and the third one is that the same R1 with third column, that is 1 into 4 plus 2 into 7. Now once that is done, you have to move to the row 2. Row 2 with C1, that is 3 into 1 plus 4 into 5. You should always come this way, top to bottom in the columns. Similarly, you have the other one is that this row 2 into C2, that is 3 into 3 plus 4 into 6. The last one is this same R2 into this 3 into 4 C3, R2 into C3, 3 into 4 plus 4 into 7. This completes my output. You can check this. You have to simplify. This is going to be a matrix of 2 rows and 3 columns. This is a matrix of 2 rows and 3 columns. That is expected because B is 2 by 2 and A is 2 by 3. Therefore, you are dropping this. These two are actually absorbing, then giving BA as 2 by 3 matrix. Hence, you have to simplify and then get it. Now, once you understand this matrix theory, what type of matrices are there to see that, and why? Are there any specific matrices? Yes, there are specific matrices. For example, you can take row matrix, which is having only one row. For example, 1, 2, 3, 4. This is a 1 row 4 column matrix. 4 columns and 1 row. 1 row 4 column matrix. Similarly, if you look at that column matrix, so which is holding only 1 column. For example, 1, 2, 3, 4. You look at this. This matrix is actually, how many rows are there? 1, 2, 3, 4 rows, 1 column. So these are the examples of row and column matrices. So row is having only 1 row, column is having only 1 column. And now there is a matrix called the square matrix. We have seen in our school math what is a square. Square is having all sizes, all sides are of same size. Square is having all sides are of same length. Therefore, whenever you define a matrix, it is of this one, same rows. The number of rows, you can say that whenever you define A, the number of rows of a matrix must be equal to number of columns of a matrix. Example, this is example. You see here the rows and columns are same, rows and columns. This is same, therefore square matrix. You can say A is m by n, again square matrix, because it is having m rows, m columns. So these are the square matrices. For example, you can say that A is equal to 1, 2, 3, 4 is 2 by 2 and B is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 by 3. But if you adjust the square matrix, or alter the square matrix, alter the square matrix with number of columns or rows, we get a rectangular matrix. That is, you can you can easily understand that why I have alteration I mentioned. Suppose A is a square, we have seen that A is having same length in all sides. Suppose you modify a bit, you are getting a matrix B, that is a little alteration, that is either you are increasing this side and reducing this. This is giving you x and y are different, therefore I have to label the other side with y. Or equivalently, I can increase the vertical length and reduce the horizontal length, then this is x, this is my y, both are not equal, that is rectangle, this is a rectangle. Therefore, whenever a matrix is having different rows and different columns, that is m and n different rows. Of course, I should not use, of course, whenever the matrix A is having the number of rows not equal to number of columns, we call A is a rectangular matrix. So you can see that row matrix where we have seen earlier, the row matrix is a rectangular matrix because number of rows are 1, columns are 4, therefore not equal, therefore it is a rectangular matrix. Here also if you look at that 4 by 1, number of rows are 4, columns are 1, therefore this is a rectangular matrix. Therefore the rectangular matrices are the matrices which are having number of rows are not equal to number of columns. Next we call it zero matrix or a null matrix. Zero or a null matrix. That is all entries, in the matrix, all entries in the matrix are zero or zeros. All elements are all entries. So you take it 2 by 2, then 0, 0, 0, 0. If you take 3 by 2, that is 3 rows, 2 columns. These are the examples of a zero or null matrix. Now we have another matrix called the diagonal matrix. Diagonal matrix. A matrix that holds non-zero entries, non-zero elements or entries in the diagonal only. Diagonal, of course we call it main diagonal. So what is that? You see here, if A is a 3 by 3 matrix, then 1, 0, 0, 0, 2, 0, 0, 0, 3. This is a diagonal matrix. This is a diagonal matrix. Again, you look back your definition, what exactly it means. You look at this particular entry, this is 1 by 1 location. This is 2 by 2 row, 2 column, second row, second column. This is 3 by 3, third row, third column. So these entries are non-zero. You look at that each one as an individual one. This location, this entry is something like, you can say that this entry is like a individual square entry, square matrix, you can see that. The rest of the entries are 2 by 1, 1 by 2, 1 by 3, 3 by 1, 2 by 3, 3 by 2. Those are non-square locations. Therefore, only row and then column positions are same. That is position in the sense that number position, that is R1, R2, R3, similarly C1, C2, C3 position. Whenever something like Ri and Ci, this should match, are the non-zero entries. We call it diagonal entries. At least one position it must be non-zero. For example, you take A is equal to 0, 0, 0, 0, 1, 0, 0, 0, 0. This is also a diagonal matrix. You can say it's a special case of diagonal matrix. So everywhere it is 0 except that the main diagonal. You have to look at that. So therefore there are special cases, but at least you should hold at least one non-zero element in the main diagonal. We call it diagonal entries. Diagonal matrix. Next one is the scalar matrix. Next one is scalar matrix. So scalar matrix, that is actually holding, it's a diagonal matrix with all diagonal entries are equal. It is a special case of, it is a special case of a diagonal matrix where all diagonal entries are same. Entries are elements same. So it must be a diagonal matrix. For example, A is equal to 1, 0, 0, 1 is a scalar matrix. Of course, we have a different name for this. We will refer that later. And B is equal to 1, 2, 0, 0, 2, 0, 0 and 0, 0, 2. This is also a scalar matrix. Scalar matrix. Now we are actually moving to the other one. Other definition is called the identity matrix. Identity matrix. Identity matrix. So we have defined already. It is a scalar matrix. It is a scalar matrix, but with one or unit is the scalar value or the constant value. That is, you can say B is equal to 1, 0, 0, 1, C is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. These are the identity matrices of different sizes. Always this is a square matrix and it must be invertible. We will see what is meaning of a invertible matrix. The next one is called the upper triangular matrix. Upper triangular matrix, and similarly lower triangular matrix. So these are, I want to just mention that these are the identity matrices. And now if you look at that, this is also a special case of some different matrices. You see that upper triangular matrices, only the entries in the main diagonal and above the main diagonal are non-zero. These are non-zero. So everywhere it must be 0. So for example, 2, 0, 2, 2, 0, 2. This is a upper triangular matrix. This is also upper triangular matrix. You can see further, you can extend that. So in other words, 2, 1, 0, 3, 4, 5, 0, 1, 3 and then 4, 5, 0, 0, 0, 3. Suppose this is one upper triangular matrix. Of course, it is 4 by 4 matrix. This is also upper triangular matrix. You have to see that. So this diagonal, that is 1 by 1, 2 by 2, 3 by 3, 4 by 4. So whether these are non-zero or not, and the above entries, at least you have some non-zero entries. It doesn't matter where it is, whether it is in 1 by 2 or 1 by 3. Somewhere it must be holding, but below the main diagonal, that means all these entries. So the below the main diagonal, or these are the entries, these must be 0. The non-zero entries must be above location. That is, one of the element is non-zero. That is enough to say that it is a upper triangular matrix. Similarly, if you look at a matrix something like that, it's a main diagonal, we have seen that, and zeros above the main diagonal. For example, you can say 0 to 0. This is lower triangular matrix, You can see further the same example. You can say that 0, 0, 0, 3, 4, 0, 0, 5, 6, 7, 0 and 8, 9, 10, 11. So you can look at this. These are actually 0 locations now above the main diagonal. So you should focus on the main diagonal. What is your main diagonal? This is your main diagonal. This is 1 by 1, this is 2 by 2, this is 3 by 3, this is 4 by 4. At least these entries, these entries. What are these entries? These entries, at least one entry must be non-zero. Then you can say that above entries, our main diagonal is sometimes one entry is enough, and then main diagonal above must be 0. Above must be, main diagonal must be 0. Then you call it a lower triangular matrix, lower triangular matrices. The last one in this, last one is the symmetric matrix. That is, A is equal to A transpose. That is, you are flipping the rows into columns and columns into rows. That is, suppose you have a matrix 1, 2, 3, 4, 6, 7. This is a 2 by 3, 2 rows and 3 columns. This is a 2 by 3 matrix. Now you are writing A transpose. According to our definition, this rows and then this is rows and columns must be flipped. So if you flip, this is columns and rows for the A transpose. That is, this whatever the number A by 3 is, A is a 2 by 3, A transpose is becoming 3 by 2 matrix. Now you have to treat that as these are the rows, these are the rows. Therefore, I am writing these rows into columns 1, 2, 6 and then 3, 4, 7. You can see this is a 3 rows 2 columns matrix, that is 3 by 2. You see, I am able to get it 3 by 2. It is called the flipping. Whenever A is given, A transpose, you have to calculate it. So this one, A is equal to A transpose, you have to, whenever these two are equal, flipping, then we call it A is a symmetric matrix. For example, you take it, A is a 2 by 3 matrix, but A transpose is 3 by 2. Both are not equal. That is, A is not equal to A transpose. This is not a symmetric. Therefore, A is not symmetric. A is not symmetric. Symmetric matrix. For example, A is equal to 1, 2, 2, 4. Then E transpose is equal to, so it is 2 by 2 matrix. If you flip it, it is 2 by 2 only. Then the rows are actually becoming columns. That is 1, 2 and 2, 4. Again same. Therefore, A is equal to A transpose. You can conclude it. A is a symmetric matrix. Therefore, A is a symmetric matrix. Symmetric matrix. A is a symmetric matrix. Now, so another example, A is equal to example 2. A is equal to 1, 2, 3. A is equal to 1, 2, 3. Then this is 2, 3 and then 4 and then 6, 8. You flip, it is a 3 by 3 matrix, and A transpose is, this implies A transpose is something like, from here you are getting A transpose is equal, therefore A transpose is equal to, it is rows you are writing as columns 1, 2, 3. Second row you are writing as a second column 2, 4, 6. Third row you are writing as a third column. Then you see here whether it is same or not. You see correspondence. First row, first column, same. First row, second column, same. First row, third column are same. These are matching. Next, you look at that. Second row, first column is same. Second row, second column is same. Second row, third column is same. Next, you are moving to the other one. Third row, first column are same. And then third row, second column, third row, third column, both are same. Therefore, from here you can say that A is equal to A transpose. Therefore, A is a symmetric matrix. Next one is called the skew-symmetric. Skew, S-Y-E, skew-symmetric matrix. Whenever you are flipping A is equal to minus of A transpose you should get. We call it a skew-symmetric matrix. For example, minus 2 and then 5 and then minus 3 and then 4 minus 4 6. What about E transpose? If you write A transpose is equal to 1 2 3, this is becoming first column, and then this is second column, that is minus 2 5 minus 4, and then third column is minus 3 minus 4, minus 3 minus 4 6. Now this is your A transpose. Now you are checking whether this is equal to, if you pull that minus outside, A transpose is equal to, if I multiply with minus sign, okay, if I multiply with minus sign, whether it is giving A transpose, whether it is giving A transpose of with the negative sign. So you look at that 1 minus 2 minus 3, of course minus 1 you are getting, and then 2 5 6 and then 4 here, of course with minus 4 is becoming plus 4, then 3 and then 4, this is becoming minus 4. Now you can see that it is actually a little difference, with a little difference it is able to give minus of A. But what is the difference here? The difference in it is the diagonals. You see here, whenever you multiply, this is actually showing some difference in the main diagonal. Therefore, I should make these entries must be 0. That is, if I redefine A is equal to 0, 2, 3, and then minus 2, minus 3, 0, minus 4, 4, 6, then A transpose is equal to 0, 2, 3, and then minus 2, 0, 4, and then minus 3, minus 4, 6. This is my A transpose. Now, if I multiply A is equal to minus of A transpose, that is minus of 0, minus 2, minus 3, 2, 0, minus 4, 3, 4, 6. If I multiply, this is becoming 0, and then minus 2, minus 3, and then 2, 0, minus 4, 3, 4, 3, 4, I'm sorry, again it must be 0. Must be 0, yeah, this must be 0. Therefore, this is exactly A. This is exactly A only. You look at that, exactly A. Therefore, A is equal to minus of A transpose, implies skew-symmetric. You see, for real matrix, all diagonal elements are 0 to be a skew-symmetric matrix. So now you can convert any given matrix, any square matrix can be written as sum of symmetric and skew-symmetric matrices. That is, if A is equal to some m by n matrix, then A can be written as A plus A transpose minus A transpose plus A divided by 2, and this is giving A plus A transpose as one set minus of A plus A transpose as the plus of A minus A transpose as other set divided by 2. So this is actually, this part is contributing a symmetric matrix. This part is contributing to skew-symmetric matrix. That is, if you write let B is equal to A plus A transpose, you apply B transpose is equal to A plus A transpose whole transpose, which is equal to A transpose plus A transpose of whole transpose is equal to A transpose plus A, which is equal to A plus A transpose, which is exactly equal to B. Therefore, this part is called the symmetric part, symmetric contribution, symmetric matrix. Similarly, if you look at the other part, that is, let C is equal to A minus A transpose. Of course, 2 is a constant, you can ignore it or you can take it outside, not an issue. Then you take C transpose A minus A transpose whole transpose, which is equal to A transpose minus of A transpose whole transpose, which is exactly equal to A transpose minus A. I can take minus common, A minus A transpose, which is equal to minus C. From there I can say that C is equal to minus C transpose. This is skew-symmetric part. Therefore, any matrix, any square matrix, you can write it as sum of the symmetric and skew-symmetric parts. So that's the conclusion from this class. We will see how to apply multiplication over 3 by 3 matrices, and then how to find the inverse of a matrix, and what are the other properties of the matrices in the next class. Thanks for watching.